Going to answer a transient problem that is a bit tricky, and I'll show it to you intuitively and also in Spice. All right, so here I have it in Spice, and I've just used 1 ohm resistors and a 1 farad capacitor. Not necessarily realistic, but the math is easy. All right, and we have a DC power supply. It's ideal at 1 volt, and we have a switch, and RN is 1 nano ohm, which you could do a pico ohm. I want 0 because I'm trying to make it ideal, but you can't put 0. It'll choke. The resistance when it's off, I put 100 meg. The VT is the transition voltage, 0.5. So you'll see that this pulse goes from 0 to 1. It changes state every 10 seconds, and it'll change state when it crosses 0.5. Hysteresis is 0. Hysteresis is some switches switch at 1 voltage going from low to high and another one going from high to low. Inductive series and voltage series, these are all non-ideal switch things that I don't want to deal with, so I've just set them to 0. So when the other thing about this simulation is I've set the initial condition on this capacitor to 0 volts. That's like saying the switch has been open for a long time and all the charge is discharged through this capacitor, right? So to force that to happen, you just tell it. So do a quick run and we'll plot some things. So this voltage should be constant the whole time, and it is. This voltage was more or less undetermined for a brief amount of time, or 0, and then went to 1 as soon as that switch closed. Right, and then if we click on switch, it goes from 0 to 1. I only ran for 5 seconds. That stays high for 10 and then goes low for, it'll change every 10 seconds. So that's pretty much my simulation window. So let's look at node 2. So we see we go from 0 to half a volt, right? And that's explained by the initial voltage was at 0, and when that capacitor fills up, no more current can flow. So we're effectively have R1 and R2 in voltage division. Since they're the same, we're going to get half of whatever the input voltage is. So that's what we get. Now, you might be thinking, it looks like it's charging a little faster than one would think. All right, that we're getting within 5 tau, right, a little sooner. And just, quick review, right, tau, it can be many things, but it can be an equivalent resistance with an equivalent capacitance. And, for some kind of step response, you would have 5 tau. Why tau? Because if I say, okay, if I have this, right, well, what is it at 5 tau? Minus 5 tau RC. And if that tau is in fact the correct RC, I have e to the minus 5. And that's just considered effectively 0, or in this case, it's 1 minus e to the minus 5. So we get there pretty closely. Right? So it's sometimes a trick. Just the way this simulation goes, it goes to 5. You might be thinking that's 5 tau. But in fact, 5 tau doesn't go exactly to where it's ultimately ended. It's just very close enough. And then we just all agree that 5 tau is what we're doing. So it's actually half, right? It's not 1 ohm times 1 farad times 5, right? It's actually half. And so it might be a little bit confusing as to where that's happening, or why that's happening, I should say. So let's come back here and just do a little warm up. So if we just have a voltage division circuit, we have R2 divided by the sum of these resistances, and there's no time because these are all ideal components. There's nothing to charge or discharge. Here, we have a resistance and a capacitance. It's a first order circuit, and the step response is 1 e to the minus t r divided by r1 c1, which in this case is tau, for time greater than 0, right? I put a step there. Now here, and doing this step is similar to closing the switch, right? I have current coming here, and some goes to the capacitor just like here, but now I have this alternate path, a parallel path for the current to flow. So really, in this case, I want some kind of equivalent resistance so that I can have tau would equal, R equivalent times that. Now, probably the easiest way to think about it, what I'm about to show you, is think about the problem differently. I have a voltage here, and this voltage is now 0. So what I do is I just short it to take it. Okay. And I can even put ground there. So now this capacitance charge can discharge here, and it can discharge there. And if you notice, I'm some current. I can take this path to this point, right? Find another nice color. Or I can take this path. So that means R1 is in parallel with R2. That means from an impedance perspective, I can do this. I can draw it like this, right? And so tau would equal R1 in parallel with R2, and I'm calling that C1. All right, and then you can go from there. Now understand, not every problem will be like this. Sometimes when the switch opens, it's a different story, but this is the generic method. If you're trying to figure out the discharge tau or any tau, set the voltages to 0 because ideally they have no impedance. They don't slow it down. And then it's much easier to see that those are in fact parallel. Seeing resistances in series like this, right, it's much easier because you can see that the current has to go through both, right? That should be a pretty good hint.